Morning, students. Today we are going to see the third unit, the last part, the model evaluation and validation techniques for assessing predictive performance. So, once we generate the model by using different types of algorithms as classified in the previous class, later we need to evaluate and validate the model. So, what is model evaluation and validation? When we build a machine learning model, we want to measure how well it performs. So, if we have created a model, then we should make sure whether the model predicts the data, okay, overfit or underfit. Okay, not just on the data we used to train it. So, it should not only measure the wow the trained data or validated data, even for the new data the model is supposed to fit well. So that is the main purpose of doing the model evaluation and validation. But more importantly, on new untrained data may be not directly fit into the model. There may be some glitches, okay, maybe overfitted or underfitted. So model evaluation and validation means measure how well the model performs, not just on the data we used to train it, but also the new data or unseen data. That's where the evaluation and validation techniques comes into picture. So model evaluation, this is about measuring how good your model is. So whether it's predicting 100% exactly as that of the relation between the independent variable and the dependent variable. Okay, for the whether the trained data or um, evaluation data or validation data, trained data or the validation data or unseen data. Even for the unseen data is supposed to fit well. Okay, we use matrix to evaluate the performance. So this depend on the type of problem. Whether for the regression model we used to check whether the model exactly fits or not. So based on the mean absolute error, mean square error, root mean square error, and the coefficient of determination, that is r square. Okay, so what are these? We might have seen these terms actually in a mathematics, okay, in a statistics. Okay, so what is mean absolute error? Is a average of absolute errors, and mean square error, it is a penalize larger errors more. So mean square error penalize the larger errors more. I will show to you an example for this different types of errors determination, and this will help you to understand whether the model fits well the data or not. Okay, so what is root mean square error? The square root of mean square error. Okay, r square, how well the model explain the variance in data. With this, I will explain and I will take chemical engineering example for all this. Before getting into the chemical engineering examples, we will see what is mean absolute error, mean square error, root mean square error, and r square score. So when you see the mean absolute error is the average of absolute difference between the actual and predicted values. So we term the actual value is yi, and yi prime, yi cap, that is a prime, just say prime is a predicted value, and n is the number of data points. MAE is equal to 1 by n summation of I is equal to 1 to n yi minus y prime. So yi is the actual value, yi cap or prime is a predicted value, n is the number of data points. So what is the interpretation over here? Gives an idea of average error. Errors are in the same unit as the data. For example, degree Celsius, bar, or it may be mole per hour. All errors contribute equally regardless of magnitude. So when we need to go for this type of mean absolute error, predicting the temperature in a reactor. For example, I want to predict the temperature in a reactor. So in that case, okay, so mean absolute error tells you an average how many degrees of your model is. Okay, so where this is an example case for the mean absolute error. So mean absolute error is the average of absolute difference between the actual and the predicted value. So how much is the average value, average of absolute? Okay, so the predicted minus actual, that will give you the error. Okay, so if the predicted value is as that as the actual value, so that will become zero. Okay, so hope you understood. So when you substitute here, actually it's supposed to be same, right? And the actual value and the predicted value is supposed to be same. And what is mean square error? Mean square error is the average of square difference. So in the previous case, we have a modulus and yi minus yi prime, that is a yi cap. Okay, here is a square difference. Mean square error is the average of squared difference between the actual and predicted values. So MSE is equal to 1 by n summation of I to n yi minus yi prime or cap square. So interpretation goes like this for this mean square error. Okay, penalizes the large error more. Okay, so since errors are squared, so that means the large penalize the larger errors. So the penalize this one is a penalize the larger errors. Okay, more sensitive to outliers. That means abnormality. Whenever you find abnormality, it will be sensitive. Okay, unit is squared. So example, so in the previous case the unit is same, but here the unit is squared. So is an example from chemical engineering perspective. If large errors are unacceptable in a chemical process, okay, for example, estimating the pressure by a big margin, MSE else penalize them more. Mean square error else to penalize that type of error. Okay, so we have seen two types of determination for regression type. Okay, so one is mean absolute error, mean square error. So MAE and MAC are important. What is a root mean square error? Root mean square error is a square root of mean square error. So the interpretation goes like this, similar to mean absolute error, but gives more weight to the large errors. But here brings the error back to the original unit. If you see mean square error, it becomes squared, and root mean square error again is come back to the original unit of the output variable. Easier to interpret compared to mean square error. So energy consumption modeling. So in that case, RMSE root mean square error shows how far off your prediction are in kilowatts. So how away we are from the prediction. Okay, the root mean square error shows how far off your prediction in kilowatts. And coming to the R square, this usually we do it in a R square value coefficient of determination. Okay, if it is 1, that is exactly fitting. For even for a linear line, we will find R squared in mathematics, right? So R square measures the proportion of variance in the dependent variable that is predictable from the independent variables. So what is the difference between dependent variable and independent variable, which I already told you. So the dependent variable is the output variable. Independent variable, let's say you have a temperature, pressure, concentration. So the reactant concentration. Let's say the dependent variable is a yield. Okay, it is a function of, okay, the flow rate, reactant concentration, catalyst concentration, and so on and so forth. So R square measures the proportion of variance. So R square is equal to 1 minus summation of yi minus yi cap square. Okay, summation of yi minus yi square. So is a value between yi minus y prime y prime. What is y prime? So yi is the actual value minus predicted value. Okay, so y bar is a mean of actual values. Okay, so in the previous cases we have seen yi is the actual value, y prime is the predicted value. So here y bar is the mean of actual values. So when r square is equal to 1, that is a perfect prediction. When r square is equal to 0, model no better than the mean. When r square is less than 0, model is worse than the just guessing the average. So the example for a model predicting the product yield, okay, in a chemical process, when r square is equal to 0.92, means the model explains 92% of the variation in the yield. Okay, I can put it in a different way in the next slide. Okay, meaning to say, okay, that all the variables, dependent variable, there is a function of independent variable. When you define all the variables, obviously the r square value will comes um, uh, higher. That the r square value comes higher, that means your model fits the data perfectly. Okay, so when it is lower, is equal to 0, is less than the, is not better than the mean. If it is less than 0, is worse than the average, that is worse than the mean. So that is the interpretation of this particular terms. Okay, when it comes for the regression modeling. Okay, so they will see an examples for all these categories. Example, predicting the reaction yield. Okay, so you are developing a model to predict the reaction yield based on the temperature, pressure, and catalyst loading. So here the dependent variable is the reaction yield. The independent variables are temperature, pressure, and catalyst loading. So here in this case the R square is equal to 0.92. The model explains 92% of variance in the reaction yield. That means your input strongly influence the outcome. Okay, that means it's correlated. Okay, so and the model captures this well. So engineers can now optimize the process parameters with high confidence using this model. So when we before we without validation, evaluation and validation, the model cannot be fit. That's why most of the empirical correlation, if you see, the errors are minimum. Okay, it's less than 15%, and if it is less than 10% error, the difference between the actual value and predicted value, most of the models has been accepted worldwide. Okay, so when you want to create a model in such a way that if it is applicable to all the conditions or scenarios, obviously your model will be uh, obviously become fail. Okay, so coming to the second part, the energy consumption in a distillation column when it is r square is equal to zero point 0.7. In that case, how we could able to interpret? So it's only the 67% of the variation in energy consumption. This decent but suggests that there are other factors which also may be included in the model. For example, ambient temperature and fouling. So what is the dependent variable and independent variable for this case? The model energy usage, that the energy usage is the output, that is a dependent variable. So feed temperature, feed composition, reflux ratio and column pressure has been given, but however they have not included the ambient temperature, fouling. So because of that factors, there may be a less value in r square. Okay, if you add these factors also, what they are trying to say, so that we could be able to predict the output, that is the energy usage, more effectively without leaving out the ambient temperature and fouling. Okay, that's what they want to mean over here. Okay, so energy consumption in the distillation column depends on not only the feed composition, reflux ratio and column pressure, it also depends on the other factors like ambient temperature and fouling. They may have a significant effect on this variable. And coming to the third example, predicting the effluent chemical oxygen demand, you are predicting the chemical oxygen demand in effluent water from a wastewater treatment unit based on the flow rate, retention time, and pH. So here, in this case, the coefficient of determination, that is R square, has been found to be 0.35 only. So what is wrong in this model? So 35% of variance in COD is explained. This model is weak. So obviously the R square value is less than 0.35, is less than the um, is less than the mean. That's what we have seen. Possibly due to the missing of important parameters as a dependent variable like microbial activity, oxygen transfer rate, or measurement noise. So the output is COD, that is a dependent variable in effluent water. Okay, the factors which they have considered, the flow rate and retention time and pH, which have some effect but not considered, is fulfill the model. Okay, because there are other important parameters, significant factors which will have an influence on COD when compared to the data which has been taken over here. For this case, the flow rate, retention time, and pH. So we also need to consider the microbial activity, oxygen transfer rate, or measurement noise, which will have a predominant effect in determining the COD value as dependent variable. So here you should not rely on this model. You should not rely on this model for real-time control or decision making, because the for the regression modeling, okay, this R square is a factor which will help you to identify, validate the model. Hope you understood. So what is the effect of R square? Similarly, the root mean square, root absolute error, square root mean square. But these are the and coefficient of determination comes into very important parameter, very important parameter under which is algorithm which is coming under the regression modeling. Okay, which are the factors which need to be considered. Okay, before we validate the model. Okay, so in the same case, even if you go for a RSM response surface methodology, we will have a statistical data where we also can see the probability, the significant effect on the variables, okay, how it has been correlated between the dependent variable and independent variable by using these variable functions like a coefficient of determination, R square, root mean square error, root absolute error. These are the factors which help you to identify the model, how well the model fits. Okay, so hope you understood. So mean absolute error, mean square error, root mean square error, and coefficient of determination, how it is important in the regression modeling to determine, to evaluate, I mean model evaluation for model evaluation. So that's what I would like to say. So hope you understood with these examples in a larger big screen how these factors is really evaluate the our model parameters, okay, modeling equation, that I can put it in that way. So if you see in a nutshell, the mean absolute error, mean square error, root mean square error, and coefficient of determination, the error type, okay, and the whether it penalize the outliers, that means the deviation from the um, maximum amount of data. So the which one is penalizes the outliers? So only the two thing, one is root mean square error as well as the mean square error. So when you have this determination like mean absolute error, whether the unit is same or is different. So in the first case and the third case, the unit becomes same because there is have a modulus, and another one is even though you have a square root, and again root mean square error nullify the square. But whereas in mean square error, the unit is squared units. Coefficient of determination R square does not have any unit. So lower is better when you have when you consider for MAE, that is mean absolute error. When mean square error, lower is better, and even for root mean square, lower is better. So which indicates the model fits very well. When you see R square, if it is very close to 1, that is exactly fit into the data. If it is equal to 0.5, average is better. If it is less than 0.5, even the it is worst. Okay, so it's less than the average. So with this note, okay, actually I just complete the for regression modeling, what are the factors which need to be considered. For the second part, I'll continue for classification models, what are the parameters which need to be tested, as that of the mean absolute error, root mean square error, coefficient of determination, R square, and so on and so forth. Similarly, for classification models, the accuracy, precision, recall, f1 square, confusion matrix, okay, reconstructing operating curve and area under the curve, that are the factors which need to be considered, okay, during the for the classification models. So when you see receiver or OC is a receiver operating characteristic curve, receiver operating characteristic curve. So we will see one by one for these cases as we did for the regression model, what are the parameters which need to be tested, okay, to validate the evaluate the model. Similarly, here the for classification models we have accuracy, precision, recall, f1 square, confusion matrix, the um, receiver operating characteristic curve, receiver operating characteristic curve, and AUC is the area under the curve, receiver operating characteristic curve. Okay, so what is accuracy? Percentage of correct prediction. Okay, and we will see an example for all these cases. What is precision? Of the predicted positives, how many were actually positive? Okay, so in the precision, usually we say it's a consistent. For example, you're throwing a arrow and then exactly fit into the thing. So it's a percentage of correct predictions. Okay, how deviate from the center point. Okay, at precision here, frequency. How many times you are just exactly throwing the throw? That is the real meaning of precision. So here, in terms of data analytics, I mean in the statistics point of view, okay, of the predicted positives, how many were actually positive? That is a um, meaning of the precision over here. So the recall is the actual positives. How many did were correctly predicted? Recall. F1 square is the harmonic mean of the precision and recall. Confusion matrix table showing true positive, false positive, false negative, true negative. So what is TP? True positive, false positive. FP means false positive. FN is false negative and true negative. Reconstructing receiving operating curve. Okay, and the area under the curve helps assess the trade-off between the true positive rate and false positive rate. I will tell you an example what is the difference between the true positive and the false positive rate in the coming slides. Okay, when you see over here the actual positive and the actual negative. So let's say we during the corona, let's say people have been for asked to test the testing whether we are positive or negative. Sometimes what will happen, actually the person will be a positive, it will the test results will show negative. Sometimes we are negative but the test results will show positive. This happened right during the corona period. So maybe people are afraid and we just go for testing because we are the next person, the person who are residing very close to us are found to be positive, or inside the house our house members are having a positive. So we were scared to find it out. For my case also it happened because my parents found to be positive. Okay, but I found to be negative. But this all happened as a true positive and true negative. So we have anyhow we could able to identify if the results shows really wrong results, then we may get confused and we could not able to diagnose the things actually, or we should not we could not we won't isolate ourselves. Obviously there is a many chances of spreading the disease in a wider way. Okay, so this is a confusion matrix. So what is the actual positive? Where the predicted positive and the actual positive is true, okay, is the same, that is a true positive. Okay, you understand, the predicted positive and the actual positive is same, that is a true positive. So it's correctly predicted. When you see actual negative but predicted positive, in that case is a false positive. Actually they are negative but the predicted is positive, so it's a false positive. Actually negative but predicted positive. Second column, the predicted negative. So actual positive but found to be a false negative, actual positive but predicted negative. So true negative means actual correctly predicted as negative. So actual as well as predicted is found to be negative, so it's true. So the true positive and true negative, in both the cases the actual and predicted are same, whereas the false negative and false positive, the actual and predicted are not same. I can put it in that way. Okay. So the confusion matrix is a table that helps visualize the performance of classification of model. It shows how many predictions were correct or incorrect compared to the actual labels. Hope you understood actually this one. Okay, and coming to the here, the accuracy, the true positive plus true negative divided by total prediction. The precision is nothing but true positive divided by true positive by plus false positive. And recall, true positive divided by true positive plus false negative. And F1 square is a harmonic mean of precision and recall. So you know what is a harmonic mean. So you have a geometric mean, harmonic mean, arithmetic mean. Okay, so log mean. Okay, so in the chemical engineering we usually find out delta T LMTD, log mean temperature difference. So when you see, okay, so even log mean pressure, the pressure difference in mass transfer, when you try to find the diffusion of A through non-diffusion B, we will have that equation, right? So these are the things actually you're supposed to know what are the different types of mean. So F1 score is nothing but a mean of precision and recall. What is the precision and recall is already tabled out with the formula: true positive divided by true positive plus false positive, and true positive divided by true positive by false negative. Okay, so coming to the receiver operating characteristic curve. What is the significance of this curve, so that we can understand, okay, what does it mean. So x-axis is a false positive rate. Okay, what is false positive rate? Is nothing but false positive divided by false positive plus true negative. So where is this false positive plus true negative comes into picture? Okay, so this is called false positive rate, that's supposed to be in the x-axis. So in the y-axis, true positive rate, and true positive divided by true positive plus false negative. So true positive plus false negative, which is nothing but a recall, right? So the y-axis is supposed to be recall, or x-axis you have a false positive rate. So it shows how the model performs changes as you adjust the decision threshold. For example, if the value is between zero point 0.1 to zero point 0.9 for a probability score. So ideal receiver operating characteristic curve starts at 0 and 0, 0, curves sharply at 0, 1 and ends at 1, 1. Shows high TPR, true positive rate, and low false positive rate is a better classifier. Okay, so area under the curve is very important. So is a significant factor for the receiver operating characteristic curve. So when it is 1, is a perfect classifier. If it is equal to zero point 0.5, no better than the random guess, and less than zero point 0.5, worse than the random. Model is inversely predictive. So the receiver operating characteristic curve, okay, area under the curve is useful in it gives a single number to summarize the model performance, works well even with imbalanced data sets, help choose the best model among the several classifiers. So these parameters, area under the curve for the receiver operating characteristic curve, will help you to identify the whether the system is perfect or not, better than the random guess or worse than the random guess. Okay, that's what it will help you to understand. So this is chemical engineering examples for this scenario. Fault detection in a heat exchanger. You are building a model to classify whether the heat exchanger is operating normally or failing. So the normal operation is considered to be 0 and faulty operation is considered to be 1. We can use sensor data to train the classifier. And the model performance, okay, you receiver operating characteristic curve and get the area under that curve is 0.91, that indicates is very close to the model perfection. Okay, so the model has excellent ability to distinguish between the normal and faulty condition. So it will help you to identify the condition whether it's a normal operation or a faulty condition. Mostly we will use with the sensor data. We can use sensor data to train the classifier. So okay, so if the area under the curve, receiver operating characteristic curve, area under the curve, which is showing only zero point 0.6, model is barely better than random. Okay, is better, but is better than random, but it's not exactly fit the data. May not be reliable for early warning systems. Okay, so it may find the false prediction as well. Okay, hope you understood what I am trying to say. Okay, so when you this is about testing how well your model will perform on unseen data. The goal is to avoid overfitting and underfitting. The overfitting means model memorizing the training data, and underfitting model too simple. So common validation techniques that we will see in the next class. There are train, test, treat, cross validation, leave on, cross out validation, stratified k-fold CV, coefficient of variance, and bootstrap validation. So model validation we see in the next class. Hope you understood now the different types of models for classifiers as well as the regression models. Okay, what are the factors which need to be considered? Okay, root mean square error, root mean absolute error, coefficient of determination. Whereas here in the classification models, receiver operating curves, okay, area under the curve, accuracy, precision, recall, f1 square, these are the factors which will help you to validate the model. So with this note, I stop it here. Hope you understood what has been taught today. I will get back to you with the remaining part of the this lecture in the shortly. Okay, thank you for listening.